In this module, we're going to work through a bunch of different examples of Lewis structures. So I'm just going to draw them all on the screen and erase, so pause as you need to, okay? First up, acetic acid. So you need to remember what the structure of acetic acid is. Remember, ic acid comes from ate, which means this came from acetate. Acetate is CH3COO minus. I need to give this enough protons, or H pluses, to make it neutral. So because it has one negative charge, I need to give it one H. Now, the reason I write acetic acid like this is because of the way the atoms are connected. Part of this comes down to just practice, okay? Hydrogen can only connect to one thing. So I have 3 hydrogens listed here. They are all going to connect to the carbon. Carbon really wants 4 bonds. The next thing listed is also connecting to that carbon atom. So the way I'm writing it is showing you how they're connected as well. Next up, I have 2 oxygen atoms. It's not that oxygen can't bond to itself, it's that oxygen doesn't prefer to bond to itself unless it's in an O2 molecule. It really doesn't like to bond to itself. So I know carbon really wants 4 bonds. One of these oxygens is going to bond to carbon. A second oxygen is going to also bond to that carbon atom. That's only going to give carbon 3 bonds, but we'll deal with the multiple bond in a minute. We have the hydrogen at the end here intentionally because the hydrogen at the end is bonded to one of the oxygen atoms. This is an oxy acid. How do I know it's an oxy acid? Because it's an acid, it's got oxygens. It's an oxy acid. So I've got C with 3 hydrogens bonded to it, bonded to another C. That C is bonded to 2 different oxygens, and one of those oxygens is bonded to a hydrogen. Okay, I've done this before. I've even added up Lewis or number of valence electrons. I'll add those up in a sec. But part of this just comes down to starting to recognize how these things are put together. Let's add it up. I've got 2 carbons. Carbon is 4 valence electrons each. I've got 4 hydrogens. Hydrogen is 1 valence electron each, and 2 oxygens. Oxygen is 6 valence electrons each. So 6 times 2 is 8, is 12. I can count. Plus carbons is 20, plus hydrogen is 24. 24 valence electrons. Okay. So far, I've used up 2, 4, 6, 8, 10, 12, 14 valence electrons. Give my oxygens their octets. 16, 18. Hold on. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So I've used up 24 valence electrons. Now I need to check to make sure all my atoms have their octet, and I see that one carbon atom does not yet have its octet. So I'm going to take a pair of electrons from that oxygen and give it the octet. Why from that oxygen? Because of formal charge. That oxygen, before I did that, had a -1 formal charge and carbon was +1. It doesn't want that. Instead, it wants to use one of those pairs of electrons to form a double bond of the carbon. Now both the carbon and oxygen both have a 0 formal charge. Remember, hydrogens with 1 bond have a 0 formal charge because hydrogen can only have 1 bond. Carbon with any combination of 4 bonds is 0 formal charge. So 4 single bonds, 1 double and 2 single, or a triple and a single, or 2 doubles would be a 0 formal charge. And oxygen with 2 bonds and 2 lone pairs is a formal charge of 0. And you have successfully drawn the Lewis structure of acetate. And then the little zeros are just emphasizing the formal charge here. Please pause the video if you need to write this down because I need to erase it to draw the next one. Nitrogen dioxide. Now, I erased this by accident a second ago. I'm not going to do nitrogen dioxide because nitrogen dioxide is going to cause a radical. Well, I mean, I guess I can do it, but I'll do it and then I'll show you why I changed it in your notes. Nitrogen itself has 5 valence electrons, and then dioxide 2 times 6 valence electrons. 12, overall 17 valence electrons. Nitrogen dioxide has the nitrogen in the center. It's the least electronegative element. Give your outer atoms their octet. And then I've used up 16 electrons. Add your extra electron to the central atom. Notice I can't add a pair there. I don't have a pair of electrons left, which is why I won't ask you to draw this one. Any sort of assessment for at least Gen Chem 1 it can come later. My nitrogen does not have its octet though. So one of my oxygen atoms is going to donate a pair of electrons to form a double bond of nitrogen. Now notice I still do not have an octet on nitrogen, but I literally can't do any more. This is the correct Lewis structure of nitrogen dioxide. Nitrogen cannot have more than an octet, and if I was to try to take away these 2 electrons and draw the octet here, that nitrogen would have the equivalency of 9 electrons, and it cannot do that. It can't go past its octet. So this is the valid Lewis structure of NO2. Again, I won't ask you to do this. I meant to change the slides and I only changed the student notes, not the slides, but let's go ahead and do dinitrogen dioxide. So N2O2 instead. Now I've got 2 nitrogens at 5 valence electrons each and 2 oxygens at 6 valence electrons each, overall 22 valence electrons. Nitrogen doesn't mind bonding to itself. Oxygen really doesn't like to bond to itself, so you're actually getting a structure like this. Again, how do you know this? Practice. The more practice you do, the more often you're going to see this, and your structures will make more sense. I've connected them, and I've used up 6 electrons so far. Give my outer atoms their octet, and check how many electrons I've used. 2, 4, 6, 8, 10, 12, 14, 16, 18. I've used up 18 electrons so far, 20, and 22. Now, my nitrogens do not have their octet yet. So what I'm going to do is I'm going to borrow from those oxygens, forming a double bond to the nitrogen. Borrow from the oxygen, form a double bond to the nitrogen. Now my nitrogens have their octet, my oxygens have their octet. Let's check formal charge. Oxygens with 2 lone pairs and 2 bonds, 0 formal charge. Nitrogen with any combination of 3 bonds. So 2 bond, just double bond and a single bond counts as 3 bonds. 3 bonds and a lone pair, 0 formal charge. This is the correct Lewis structure of dinitrogen dioxide. Okay, oxalic acid. So remember again, ic acid comes from 8. Oxalate is C2O42 minus. So oxalic acid would be H2C2O4 because I need to give it 2 H pluses to counteract that 2 negative charge. 2H, each hydrogen has 1 valence electron. 2 carbon, each carbon has 4 valence electrons. And 4 oxygen, 4 times 6 valence electrons. So 4 times 6 is 24, plus 8 is 32, plus 2 is 34. Again, part of this comes down to just practice, but the way this is connected, my carbons like to connect to each other, but oxygens do not like to connect to each other. It is an oxy acid. I know that because I have oxygens and hydrogens both present in an acid, and they're almost always connected to the oxygen atoms. Not 100% of the time, but if they were not, I would give you more clues about that until Chem 2. And then the extra oxygen is connected here. Give your oxygens their octet. And check your electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34. I've used up all my electrons, but my carbon atoms do not yet have their octet. So I'm going to use the oxygens that are singly bonded because I know they do not have a 0 formal charge. I'm going to use those to give those carbon atoms in the center their octet. So I'm going to take a lone pair from here and make a double bond. The lone pair from here and make a double bond. Now my hydrogens have a 0 formal charge. They have a single bond. This oxygen is 0 formal charge, 2 bonds and 2 lone pairs, as is this oxygen. This oxygen also has 2 bonds and 2 lone pairs. It's just a double bond, as does this 0 formal charge. And each carbon atom has a 0 formal charge because they each have 4 bonds, 2 single and 1 double. What about perchlorate? ClO4 minus. So Cl, 7 valence electrons, 4 oxygen, 4 times 6 valence electrons, plus 1 extra electron due to that -1 charge. So 4 times 6 is 24, plus 8 is 32. Chlorine is less electronegative than oxygen, so it's going to go to the center. And I'm going to connect my oxygens. I'm going to give all my oxygens their octet. I gave them all their octet. Now I'm going to check formal charge. Each oxygen here, remember formal charge for 6 valence electrons, it has 6 lone electrons on it and 1 bond. So each oxygen is showing a -1 formal charge right now. And the chlorine, 7 valence electrons, no lone electrons, and only 4 bonds, is showing a +3. We know that's not going to happen because there's ways to minimize it. We can give it multiple bonds. So let's say that this oxygen on top donates a pair of electrons. Carbon now has 5 bonds. This oxygen is now a 0 formal charge because, again, 2 bonds and 2 lone pairs is 0. But chlorine now has a +2 formal charge. Well, that's not going to work. Let's keep going. Give it another double bond. Now this oxygen has a 0 formal charge. Carbon has a +1 charge. Not going to work. We can still minimize that. How about right here? Give this one a 0. The chlorine now has a 0 formal charge. So chlorine can do this because it has an expanded octet. Because it has empty d orbitals, because it's in the n=3 energy level. It has empty d orbitals it can put those electrons into, so it can have more than its octet. It has space to hold the electrons. Not only does it have the empty d orbital, so it has a space there, but it has the physical space, like the radius of the atom has the space to accommodate more than just 4 bonds. Oxygen, nitrogen, and fluorine cannot do this. Overall, the formal charge is still -1. Oxygen right here is -1, and the perchlorate ion is -1. This is the correct Lewis structure. What azide? Azide is N3 minus. So 3 nitrogen, 15 valence electrons there, plus 1 extra valence electron, 16 valence electrons overall. Connect them and give your outer atoms their octet. 2, 4, 6, 8, 10, 12, 14, 16. I've used up all 16 electrons. But my central atom does not have its octet yet. So what can I do? Well, I could take the pair right here, take a lone pair here, make this, right? Still doesn't have an octet. Could take a lone pair here and do this. Now the central atom has its octet. Let's check formal charge. We're going to call this N1, N2, and N3. N1 and 3 each have 4 lone pair electrons, or 4 electrons involved in lone pairs and 2 bonds. So each one of these is a -1 charge. And 2 in the center, 5 valence electrons, no lone pairs, and 4 bonds, a +1 charge. So overall, it matches. Overall, -1 plus 1 plus -1 gives me that -1 charge. I cannot further minimize this. Nitrogen cannot have more than 4 bonds. It cannot have more than its octet. So the outer atoms can't do anything, they can't share anymore, and the central atom can't do anything because it has its 4 bonds. Here's the trick though. Remember when I grabbed it, I grabbed a pair of electrons from each nitrogen atom. What if I had grabbed them all from the same nitrogen atom instead? This is your resonance structures. I don't have space to write this in the exact same spot, so I'm gonna have to write them down instead of across. But what if I instead did a triple bond here and a single bond here? Or a single bond here and a triple bond here? All of these are valid Lewis structures. They're all following the rules of Lewis. Let's check formal charge on each species. We know nitrogen when it has 4 bonds and no lone pairs has a +1 charge because we just figured that out above. We know the nitrogen with 4 electrons in lone pairs and 2 bonds has a -1 charge. And 4 electrons, 2 bonds, -1 charge. Okay. We know when nitrogen has 3 bonds and 1 lone pair, it's a 0 charge. So let's check this other nitrogen down here, the one that has 1 single bond and 3 lone pairs. 5 valence electrons, 6 electrons in lone pairs, and 1 bond. Notice these are valid Lewis structures, but these are not minimizing formal charge. What that means is these will contribute the least equally, whereas this structure will contribute the most. Now, sometimes you'll get 3 different structures. So one is like least, one is middle, one is most. In this case, 2 of them are equivalent, but they contribute the least because I've not minimized the formal charge. Where am I? Let's see. I'm going to start crossing them off because I'm going to forget where I'm at. Chlorite. So chlorite is ClO2 minus. 7 valence electrons, 2 oxygen times 6 valence electrons, and 1 extra valence electron for the negative charge. So 12 plus 8 is 20 valence electrons. Give your outer atoms their octet. I've used up 16 electrons. $18 and $20. Everyone has their octet. Let's check formal charge. Oxygen, 6 valence electrons, 6 lone electrons involved in lone pairs, and 1 bond, -1. The chlorine, 7 valence electrons, 4 electrons involved in lone pairs, and 2 bonds, plus 1 charge. Now, it can minimize this formal charge by forming 1 double bond. So let's do it. If I do that, oxygen, remember when oxygen has 2 bonds and 2 lone pairs, it has 0 formal charge. If I check the chlorine now, 7 valence electrons minus its 4 electrons involved in lone pairs minus its 3 bonds has a 0 formal charge. So we just drew this. But there is a resonance structure. I'm not going to have enough room here. Trying to force this in here. That is a negative charge there. These are resonance structures. But in this case, these resonance structures are equivalent. How do I know that? Because if I do the formal charge here, I get a 0, and a -1, -1, 0, and 0. Notice that they both have the same amount of formal charge, 2 zeros and a -1, and the -1 is on an oxygen atom. They're equivalent resonance structures. Let's look at bicarbonate. I know carbonate is CO3 2 minus, so bicarbonate must be HCO3 minus. I've got a hydrogen, so 1 valence electron. I've got 1 carbon, 4 valence electrons, 3 oxygen, 3 times 6, and 1 extra valence electron for charge. So 18, 19, 20, 21, 22, 23, 24 valence electrons. Bicarbonate is amphiprotic, meaning it acts as an acid and a base. It can accept a proton or it can donate a proton. Does that because it acts as an oxyacid, which means that that hydrogen is bonded to an oxygen atom. Connect them all and give your oxygens their octet. I've used up all 24 electrons. Everything has an octet right now except the carbon. So I'm going to go ahead and take one of those lone pairs from one of the oxygen and make a double bond to the carbon atom. Now, why did I do to that one? Because it was there. I could also have easily just drawn it Single bonded over here, double bonded here. And some students will say, well, isn't that exact same structure? Not if you number the oxygens. It depends, is your double bond to oxygen 1 or oxygen 3, the way I've numbered them. Go ahead and look at your formal charge. Oxygen with 2 bonds and 2 lone pairs is 0. Carbon with 4 bonds is 0. Hydrogen with 1 bond is 0. This is my -1, and overall it is a -1 charge, so that is the correct Lewis structure of bicarbonate. Butane, C4H10. Okay, it is an organic molecule, and here's the trick with organics. Carbon really likes to bond to itself. So what this does is it's going to form a carbon chain with the hydrogens connected. How do I know that? Because hydrogen can only have 1 bond. And if hydrogen bonds to itself, it's just H2. There's nothing else there. I don't know why I drew that over there. Let's put this back over here. If I look at this, I've used up C4H10. If I add up my electrons, 4 times 4, 16, plus 10 is 26. I've used up all 26 electrons. Every atom in there has a 0 formal charge. Every carbon has 4 bonds. Every hydrogen has 1. Ethanol, CH3CH2OH. Again, this is showing you how it's connected. It's saying I've got a carbon with 3 hydrogens. I've got a second carbon with 2 hydrogens. I've got an oxygen with 1 hydrogen. Give your oxygen its lone pairs for its 0 formal charge. If you add up the valence electrons, let's see, 2 carbon is 8 plus 6 hydrogen is 14 plus the oxygen is 20. If you check this structure, you're going to find that it used up 20 valence electrons. Okay, next up, propene. Okay, the formula listed is actually not propene, so let's fix that. The formula listed is actually for propane. I'll show you propene in a sec. But first, let's do propane. This is showing me I have 3 hydrogens connected to the carbon, 2 hydrogens attached to a carbon, 3 hydrogens attached to a carbon, and the carbons all attached to one another. So I have 3 carbons in a row. And that's my Lewis structure. 3 carbons times 4, 12 plus 6 hydrogens, overall 18. And if you add that up, you should have used all 18. Now, propene would have the formula CH2CHCH3. Propene is a little bit different. I meant CH2. So propene would have the carbon with 2 hydrogens, another carbon with 1 hydrogen, and another carbon with 3 hydrogens. But notice that 2 of my carbons right now do not have their octet. I fixed that by giving it a double bond. And so we'll learn about organic structures next semester, but the ene tells me there's a double bond present. And that's how I knew the formula was wrong, because it had too many hydrogens present. So this is the formula of propene. If you add it up, 3 carbons, 12 plus the 6 hydrogens, overall 18 valence electrons, you've used your 18 right here. Cyanide, Cn minus, 4 valence electrons from carbon. Nitrogen, 5 valence electrons, plus 1 extra valence electron, overall 10. So your carbon and your nitrogen, I've used up 8, I've used up 10. Now I need to give both atoms their octet. Carbon does not have an octet yet, so I fixed that by making a triple bond. Now both of them have their overall octet. If I checked formal charge here, though, nitrogen has a 0 formal charge, but if you add up the formal charge of carbon, you're going to see it's a -1. And that's why cyanide itself has an overall -1 charge. We see that come through in the structure and in the Lewis structure and in the original actual compound itself. Like the ion itself has a -1 charge to it that can be measured. Hypobromide. Hypo means Bro minus. So bromine, 7 valence electrons. Oxygen, 6 valence electrons, plus 1 extra valence electron. Overall, 14 valence electrons. I've used up 8 so far, 10, 12, and 14. Now, if I check the formal charge, bromine is a halogen. If halogens have one single bond and 3 lone pairs, they have a 0 formal charge. Oxygen, 6 valence electrons, minus 6 electrons in lone pairs, -1, gives me an overall -1 charge in the oxygen, but the hypobromide has a -1 charge. This is the correct Lewis structure of hypobromide. Nitrate, NO3 minus, nitrogen, 5 valence electrons, 3 oxygen, 3 at 6 valence electrons each, and then 1 extra valence electron for that negative charge. 3 times 6 is 18, plus 5 is 23, plus 1 is 24. Nitrogen's going to go in the center. It's the least electronegative. Give your outer atoms their octet. Now I don't have any electrons left over, but nitrogen needs its octet. So I'm going to pull from one of the oxygens to give its octet. If I looked at formal charge here, 0, +1, -1, -1. Overall, still a -1 charge. -1, -1, +1 gives me an overall -1. Now there is resonance here. So you should look at the key. But again, for resonance structures, we typically draw them into the boxes, putting its charge up here. And then we use resonance arrows to distinguish between them. But space is an issue on the screen. So I could draw the double bond to any of the other oxygen atoms. So nitrate has 3 overall resonance structures. The more resonance structures, the more stable the ion or molecule or whatever it is. So this is more stable than something like nitrite because it has 3 resonance structures. Now, all of these contribute equally. They're all equivalent structures. They all have 2 oxygens with a -1 charge and 1 oxygen with a 0 charge. What's up next? Hypochlorous acid. Hypochlorous, us comes from ites. This is coming from hypochlorite, which is ClO minus. So this means HClO. Hydrogen, 1 valence electron. Chlorine, 7 valence electrons. Oxygen, 6 valence electrons. Overall, I can't count. Yes, 14. I was right. 14 valence electrons. It is an oxyacid because I have an acid with an oxygen in it, so therefore it is going to be an oxyacid. 8, 10, 12, and 14. Halogens with 1 bond and 3 lone pairs have a 0 formal charge. Oxygen with 2 bonds and 2 lone pairs have a 0 formal charge. Hydrogen with 1 bond has a 0 formal charge. Phosphorus tribromide, EBr3. Phosphorus, 5 valence electrons, 3 bromides, or 3, and bromine has 7 valence electrons, so 3 times 7, 26 valence electrons overall. Phosphorus to the center, it's less electronegative than bromide, plus there's only one of them, so that's kind of the other cute clue to it. Give your outer atoms their octet. Extra pair of electrons to the central atom, because I'd only used up 24. Now that's 26. Halogens with 3 lone pairs and 1 bond have a 0 formal charge. Phosphorus is like nitrogen. 3 bonds and 1 lone pair, 0 formal charge. See, chlorine trifluoride, ClF3. Cl, 7 valence electrons. 3 fluorine, 21 plus 7, 28 valence electrons. So Cl, F, F, and F. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, and 28. There's 2 lone pairs in that central chlorine. Now remember, fluorine can literally not have more than one single bond. We don't talk about it as an exception, but it is the truth. It has no space for more bonds because it's in the N=2 energy level. So it cannot do any more. It is stuck. 0 formal charge as well. Fluorine, 7 valence electrons, 4 electrons in lone pairs, and 3 bonds. Overall 0 charge there as well. Phosphite, VO3, 3 minus. Phosphorus, 5 valence electrons. 3 oxygen, 3 times 6 valence electrons, and an extra 3 valence electrons for that -3 charge. So 18, 19, 20, 23, 26 valence electrons. I've used up 24 electrons and put the extras on that central atom. Now, if I look at this, phosphorus is quite happy. Each oxygen is a -1 charge. There's not going to be a double bond here. There's no need for it. Phosphorus doesn't need a double bond. It's completely happy octet. It's got a 0 formal charge. It's going to stay as is. Each oxygen being a -1 charge actually contributes to the reality of the real structure, where I have an overall -3 for this species. So this is phosphite. Propanoic acid, another organic compound. So again, hydrogen's connected to the carbon, hydrogen's connected to the carbon, oxygen and oxygen connected to carbon, hydrogen connected to oxygen. How do you know? Practice. Carbons connected to each other. So I've got 3 carbons in tow. One of those carbons has 3 hydrogens attached to it. One of those carbons has 2 hydrogens attached to it. One of those carbons has 2 oxygens attached to it. And one of those oxygens has a hydrogen attached to that. If you add up all the valence electrons there, let's see, 3 carbon, 12, plus 2 oxygen, 24, 25, 26, 27, 20, 20, 30 with the hydrogens on there. Give your oxygens their octets. Let's see, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. I've used up all 30. But notice this carbon right here is missing its octet. I'm going to fix that by giving it a double bond from that oxygen, using one of those lone pairs to give it a double bond. Now, if I look at the formal charge of everything, all my hydrogens will be 0 because they all have one single bond. This oxygen is 0. It has a double bond and 2 single bond, or a double bond and 2 lone pairs. This oxygen has 2 single bonds and 2 lone pairs. And each carbon has a combination of 4 bonds, 2 of them having 4 single and 1 having 2 single and a double. Overall, 0 formal charge. CH3, CH2O, CH3. Again, hydrogens attached to the carbon, hydrogens attached to the carbon. Oxygen is going to be trapped. It's going to attach to both of these carbons. Hydrogen attached to the carbon. How do you know? Practice. The way the molecule is written is showing you how it's connected. CCOC, 3 hydrogens, 2 hydrogens, 3 hydrogens. And if you add up your valence electrons, you're going to see you have just enough to give oxygen its octet with its lone pairs. Oxygen will always get its octet with its lone pairs. It's quite happy to do that, and it's always going to get its way. Ethine, HCCH. So H to C to C to H. If you add the valence electrons, you'll get here as well. But even if you look at this, you can do this. You should be able to do this, relatively speaking, without even looking at the number of Lewis structures to it. I mean, sorry, number of valence electrons to it. Hydrogen can only have 1 bond. Each carbon needs 4 bonds. It only has 2, 3, and 4. Putting a triple bond in the center will make that work. So SO2, Cl2. Okay. 1 sulfur, 6 valence electrons, 2 oxygen, 6 each, and 2 chlorine, 7 each. 14 plus 12 plus 6, 32. 32 valence electrons. Sulfur is the center and attached to everything else. How do I know that? Part of it comes down to practice. Part of it comes down to organic compounds. I will always tell you the structure that they're written out in. So the way these are written, these are organic compounds, and they're showing you the way they're connected. The other ones, you'll have one central atom or an oxyacid, but you need to recognize they're oxyacids by the hydrogen oxygen being present. Otherwise, everything's really going to be attached to the central atom. Give your outer atoms their octet. Check your central atom. Your central atom does have an octet. Check your formal charge. Can you minimize that? 100%. Let's not give away, let's donate one of these pairs of electrons from a double bond here. Now I got +1, -1. I can fix that. I've got 0, 0, and 0. How do I know I can do that? Sulfur has an expanded octet because it's in the n=3 energy level. So it empty d orbitals, and it's physically large enough radius-wise to hold extra electrons. XeOF2. Xenon, 8 valence electrons. Oxygen, 6 valence electrons, 2 fluorines, 2 times 7. 14 plus 6 is 20 plus 8, 28. Xenon in the center. Give your outer atoms their octet. Oops. I've used up 24. Or I've used up 2, 4, 6, 8, 10, 12, 14, 15, 18, 20, 22, 24. Yes. 24, 26, and 28 to the central atom. If I look at formal charge now, my fluorines are 0. This oxygen is -1. My xenon, 8 valence electrons, 4 electrons in lone pairs and 3 bonds, has a +1 charge. I can minimize that by donating one of these pairs of electrons to form a double bond to the xenon. Xenon is able to do that because it can have an expanded octet because it's greater than the n=3 energy level. Next up, AsO3 minus arsenate. Arsenic is under phosphorus, so 5 valence electrons, 3 oxygens at 6 valence electrons each, plus an extra 3 valence electrons for charge. So 18, 23, 24, 25, 26 valence electrons. Give your outer atoms their octet. I've used up 24. Add your extras to the central atom. Now, everyone has their octet. Check formal charge. -1. Keep hitting the screen. -1, -1, and 0. That is the correct structure for arsenate. EOCl3. Phosphorus, 5 valence electrons, and oxygen, 6 valence electrons, and 3 chlorines, 3 times 7 valence electrons. 21 plus 5 is 26, plus 6 is 32 valence electrons. Phosphorus, oxygen, chlorine, chlorine, chlorine. Again, how do I know they're all connected to the central atom? Because I can tell it's not an organic molecule. With organic molecules, they're more drawn out. They look like this. They have lots of carbons, lots of hydrogens, lots of oxygens. So it's phosphorus and chlorine in it. Practice, lots of things kind of go into just kind of knowing that. Give your outer atoms their octet. Everyone has their octet. All my electrons are used up. My central atom has an octet. Let's check the formal charge. -1, -1, -1, -1 plus 1. Or sorry, not -1's here. Zero's here. I was thinking about oxygen and writing. There you go. Zero's here. -1 on the oxygen, plus 1 on the phosphorus. But I can fix that. Double bonded here. Everything is 0. So POCl3 looks like this. Again, the Lewis structure doesn't have the formal charge throughout the whole thing, but you need the formal charge to identify if it's the correct structure or not. ClBr3. Overall, chlorine has 7 valence electrons, bromine has 7 each, and there's 3 of them. So 7 times 4 is 28 valence electrons. Cl is going to be my central atom here. Why? It's not, it's the most electronegative. You're right, it is. But it's going to be the central because it's the first one listed and it's the only one that there's one of. And that's the kind of hint that gives me the idea that it's a central. Connect them all and give your outer atoms their octet. I've used up 24 electrons, 26, and 28. Notice how I do that when I need 2 pairs in the central atom, but they can't be next to each other. I kind of draw them at angles on each side. What I'm not going to do is I'm not going to draw them like this, and I'm not going to draw them like this. I'm going to emphasize that it's 2 separate pairs by drawing one on either side of the top of that chlorine. Now check the formal charge. Halogens with 1 bond and 3 lone pairs have a 0 formal charge, so bromines are easy. Check my chlorine, 7 valence electrons, 4 electrons in lone pairs, and 3 bonds. Overall 0 formal charge, so that is the correct structure of ClBr3. And this last one's going to take a little more space than we have. S2O32 minus. Let's see. 2 sulfurs, 12 valence, or 2 sulfurs, sulfur has 6, oxygen has 6. So 5 times 6 is 30, plus 2 is 32 valence electrons. You have a sulfur in the center, connected to 3 different oxygens and a sulfur. Give your outer atoms their octet. Your central atom has its octet. Check your formal charge. I can minimize that. How do you want to minimize it? Boys. Let's go ahead and donate a pair of electrons to share here, and a pair of electrons to share here. That's one resonance structure. It's a great one. And I could do that any combination with the other oxygens. I'm not going to draw them all out. You can see it in the key that's posted. But you could see that, you could do this all out with any other combination of making 2 oxygens. But you could have also done this with the sulfur. There's no reason why you couldn't say, I want to double bond to sulfur, and then double bond to one of the oxygens. Check the formal charge here, 0, -1, -1, 0, and 0. So again, when you do resonance, you're supposed to put them in brackets to charge negative overall, arrows in between the different structures, etc. But what I want you guys to think about is if you had these two structures, I just cut that off, it's -1 right there. Which one would contribute most? What do you guys think? Let let me shrink this down a little bit. So if I look at these two structures, they're both a 2 negative charge overall, okay? Both of them have sulfur in the center with a 0 formal charge. Both of them have one of them has one oxygen with a 0 formal charge, one has two. Both of them have two different atoms with a -1 charge, but which one's going to be best? Meaning contributes the most. Which one contributes the least? They're not equivalent. So how do I determine it? I look at who has the formal charge. In this species, the two formal charges are on oxygen atoms, which are more electronegative than sulfur. Here, one of the negative charges on a sulfur, one is on an oxygen. This is going to be most favored. This is going to be least because it wants, if it has to have the negative charge, it's fine, but it wants the negative charge on the more electronegative element when possible. And in this case, it's possible on this structure here. So this will contribute most, this will contribute least. Now, again, these are not the only two resonance structures. I could flip around where the double bond is to the other oxygens for both of them. This one, I could see that happening on this structure or this structure. So there are a lot of resonance structures though, but that means that this ion is very